Hello, math magicians. On this day, we're going to continue assignment number 3. We're going to do page 2, and we are going to look at the dumpster fire of graphing and zeros and x-intercepts. So, don't worry, we're going to call in an expert who knows how to put out the dumpster fire. This is Rescue Squad Smokey, and he's here to help us out. Yay! Thanks for helping! No problem. I'm here to save the day. Woo! Please do so. Thank you. So, let's attack, kill, and destroy. The first concept, read with me, as we look at a key concept about roots, zeros, and x-intercepts. In fact, this is review based on stuff that we did with quadratics. So, let's read through it. The following are equivalent statements about a real number b and a polynomial p of x. A sub n, x to the n, plus a sub n minus 1 times x to the n minus 1, plus dot, 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 and it follows that pattern all the way. Now, before we panic about that, let's just double check to see what the pattern is here. So, looking first, the a sub n simply means, and the a sub n minus 1, simply means the coefficient. The coefficient. You know, like 2, negative 1, positive 1, decimals, fractions, etc. So these are just the coefficients right here. And all we're saying is this is the primary one, and this is the one in the front, second one, and this one right here, a sub 0, is a constant because there's no variable there. Now, let's look at the second pattern before we panic. This one says to the nth power. This is the n minus 1th power, and this is the 1th power there. And notice there is no x over here, so that's x to the 0 power. So what's the pattern here? What we're doing is, for example, x to the 3rd, x squared, x to the 1, and x to the 0. So in other words, just to point this out, this form right here is standard form. Standard form. And let me just show you what that might look like. Right, so we have some function y is equal to 3x to the 4th plus 5x to the 3rd minus 8x squared, dot, dot, dot. So just to show you, notice it goes 4, 3, 2, down, and the 3, the 5, and the negative 8 have no relationship with each other. Okay, there's no pattern necessarily with those. We're simply stating that this is the coefficient on the quartic term, this is the coefficient on the cubic term, etc. All right, now, what are we saying here? We're saying that x minus this b that we talked about, the b being a real number, x minus b is a linear factor of the polynomial. Now, usually we see x minus b in parentheses, like so, and I want to give you an example here. See, the x minus some number here. So this here would be a linear factor. Now, why is it called linear? The reason for it being called linear is the fact that this is raised to the power of 1 right there. So it's a linear factor. Next, when we have a linear factor, x minus b, then here are the 3 things that are true about b, or 4 actually. That b is called my 0, so notice it's the opposite of what I see. If I see a minus 3, then I'm going to put a positive 3 right here. Then b is a 0 of the polynomial function. What does that mean? It means that when I put in that number, b, into the function, but here and in all the x's, all of this becomes a 0. Another thing, b is called the root or solution of the polynomial equation. And lastly, when we graph it, b is the x-intercept of the graph of the entire function. So let's summarize real quick. What we see here, and this is essentially true, which is why I've said they are pretty much synonymous here, so not perfectly synonymous, but here we have that roots and zeros, and there could be more than one, which is why I'm putting parentheses there, or solutions, and I'm abbreviating that right there, solutions or x-intercepts. When we're talking about a function or an equation related to that, they're all derived from these linear factors, and there could be more than one. They're pretty much synonymous. And x minus b, which is called a linear factor. Okay, so let's see how that applies. What we're saying is that the zeros are also the x-intercepts. So if I can find out what each of the zeros here are, that means I can use it to graph fairly quickly. So let's look at example number 3 here. Finding zeros of a polynomial function. So what are the zeros of this function right here? And then we're going to graph the function. So part A, we're going to use the linear factors and the zero product property to find the zeros. Now, what does zero product property mean? The zero product property, of course, means this. If I have A times B equals 0, we know that A is 0 or B is 0. So whenever we have a product that multiplies to 0, one of those numbers has to be 0. At least one of them. All of them could be. So we've already seen that when we were solved quadratics by factoring. And what we're saying is this here, is that we have a factor here, and a factor here. And according to the zero product property, either this factor is equal to 0, this factor is equal to 0, or this factor is equal to 0. And that's the zero product property. It means that we can split everything up. Okay, so we have one of the zeros right here. It's a 0. The other 0, we add 2 to both sides to get a 2. And the last 0 here, we subtract 5 from both sides to get negative 5. So that means my zeros are, one of my zeros happens to be a 0, another 0 is a 2, and another 0 is a negative 5. So what does that mean? Well, my zeros, remember, are synonymous with the x-intercept. So that means 0, 2, and negative 5. 0, 2, and negative 5 are my x-intercepts. So here's 0. Negative 5 is right in the middle here because we're counting by 2's. And lastly, positive 2, which is right here. Now, I don't know what my graph does here. I don't know if it's going to start low like this and come up like this and come down and then come up and bounce off this and come back down. We don't know yet, so I need to examine that using end behavior. Okay, so let's look over here. Remember end behavior. How did we determine end behavior? And end behavior was this. When we had things in standard form, we had to look at the very first term, the leading coefficient. And these components told me something, that when n was even and x was, and a is greater, so we have a positive number here, that means we have up, up. So something like this, right? Up, up. That means end behavior, it starts in the up and then ends in the up. All right, and the same thing applies here, but we flip it. So instead of up, up, this flips to down, down. So those are my two options when n is even. When n is odd, we're going to get more of a situation like this, where we have a line like this, or we can have a curve like this, or it can even get, crazy like that. But the point is, it starts low, ends high, or we can flip it, depending on the value of a. So in this case, if n is odd, then we're going to start low, and a is positive, we end high. In other words, this increases as we read it. It starts low and goes up, 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 up. So up, 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 up. Up, 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 up. This could have a little bit of waving, but it starts low, ends high. All right, so if a were negative, then it flips the other direction. So this one would start high, end low. Okay, So the question is, how do we determine end behavior when this is not in standard form? When this is not in standard form. So that's okay. All we need to do is find the very first term. So what's the first term? Well, the first term is this times this times this. It's all my variables multiplied together. So end behavior is based off of x times x times x. So I get x cubed. So two things here, that this is a positive 1 right here, and this is odd. So let's look at my chart over here. We have a positive 1 here, and we have odd. So it starts low, ends high. So what's my end behavior? My end behavior is down, up, or starts low, goes high. So practically speaking, what's that mean? It means that my equation or my graph is going to start somewhere down here and end up over in here. And in between, it's going to do a few things. So it's going to start somewhere in this ambiguous area, come up. It has to pass through this. I don't know how far up it goes. It goes all the way up, or it could go here. But it's got to come back through this, or at least touch it. It might bounce off it, but it touches it. And then it's got to come back and touch this somehow. Okay, so foom, 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 something like that. Okay, so the real question is, well, how far up does it come here between these two zeros? And how far down does it come here between these two zeros here? We don't know the behavior inside. We do know where it crosses, and we do know where it starts and ends, but we don't know some of the details in between. So what we're going to do now is find some additional points. So we need to see the behavior of the function between these two numbers right here. So just to remind ourselves, this here is a 0, and this one's a -5, and this one's a 2. So I want to choose some number, and we're going to go with a nice number between 0 and -5. So let's just throw out negative 3. So what happens at -3? Now over here, what's a nice number, the nicest we can get between 0 and 2? Well, directly in the middle is a 1, right? So I am going to come over here, and I'm going to use x is equal to +1. All right, so when I substitute a -3 into my original function here, I'm going to see how high it goes or low it goes, depending on the context. Okay, so let me substitute some things in here. All right, so let's substitute a -3 in. So -3 here, -3 here, -3 here. So I get -3 times a -5 times a +2. And in the end here, we get 30. So now we have a new point. The point is -3 +30. -3 +30. So that means way up here, -3, of course, lives, here's 2, so here's -3 right there, all the way up to a +30 there. So now we have a point. We see the behavior of this function between those two zeros. So far, it starts low somewhere here. It's got to pass through this point, come all the way up to there, and then zip back down here. And we don't know how low it goes here. So that's what we're going to do on the next one. Now I'm going to plug in a 1 and see what happens. So plug in a 1 here, 1 here, and 1 here, and see what we get. So y is equal to 1 times a -1 times a 6. So here we end up getting a -6. So how does that affect things? Well, it's going to go down to a -6. So let me just check my scale here. This is a -10, so -2, -4, -6 is there. And that's happening here at the 1. So I've got to go between the lines right here. Now, I don't know if this is the lowest it goes, the line. I'm just going to sketch real quick how this line might go. It might do this, where it comes down and then comes steep up here and through there. And it might go even further down. We don't know if this is the lowest or not. So I can't assume that, but we know that it's probably about right. Okay, so the question is, how are we going to manage and graph this? Okay, it's going to take an eraser. So my suggestion for you is to sketch with a pencil. I have undo buttons here that I can do. So I'm going to start somewhere down here, but notice I've got to get pretty steep because it's got to go through this thing, and it's got to go all the way up to here and maybe even higher. Don't know. And then it's got to come back down, and then it's got to pass through this, come here, come up, and notice that my cloud is probably in the wrong place right here. So it looks like it's going to do that. Now, I don't know if that's the exact function, but it certainly looks pretty darn good. So I'm going to now commit to it by actually passing through my dashed lines, clean that up a little bit. Again, use an eraser if it's not very clean, and the curve should be very curvy. And these parts aren't necessarily lines. It's still going up, 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 and curving a bit. Okay, so I'm going to put arrows on either end, and there we go. Now let's go ahead and check this using a graph. So here's Desmos, and I've entered the function in, and of course notice what we get here is it's quite off, so I need to of course change my scale to C, and notice here that at -3 it goes actually a little bit higher than what we were expecting. But here's some things that we know to be true. Number one, my zeros are correct, -5, a 0, and a 2. And we notice that at slightly bigger than 1, it goes down lower than -6. So we were pretty good there on that estimate and pretty good here on this estimate. Now we're just sketching it, so we don't have to worry about the fact that this is higher than ours is and in a different place. We're just looking for a rough sketch here. So let's compare, and we do see that although the scales are different, we see the major points are true. It starts low, ends high. It passes through these 3 x-intercepts, and its highs and lows in the relative highs and lows are actually pretty close to those ones there. So the basic shape is correct. Clearly, I need some work on, because look at how smooth those are. My curves here aren't so smooth. Okay. Now it's your turn to practice this. Again, find your zeros right here and plot those. Number 2, determine what the end behavior is by multiplying x times x times x. And determine, does it start high, end high, start low, end low, start low, end high, or start high, end low. Those are your 4 options. And next, find some additional points. Between your zeros, you have to choose some nice number that you can plug back into the original problem and find the approximate behavior of what happens between the zeros. Go ahead and check your function using Desmos or your TI calculator. Thank you very much. Yay, you saved us!
You're right, I did.
Mwah! I love math!